0. And later it can launch its own guest and assign ACID1 to this guest. So we have to handle this situation, and we should update VMCB1 prim accordingly. So we have to control what ACIDs have been assigned and what are free. So if we support this tagged TLB feature, we have to implement these algorithms for modifying ACIDs as well. A few words about performance impact. As you saw in a general picture about the nested virtualization for AMD, it introduces only one VM exit on every original VM exit that should happen in the system. Also, we have to intercept STGI, CLGI, vmload, and vmsave instructions, in addition to vmrun, for example, which is obligatory intercept. We also have to intercept everything that nested hypervisor intercepts, of course. We have lots of optimizations space here. So I will show the picture about performance impact later when I discuss paravirtualized domains on AMD. What about Intel? There is no global interrupt flag on Intel, so it's a bit simpler to implement nested virtualization on Intel. There is no tagged TLB support right now, no ACID conflicts too. But VMX instructions take different type of arguments. They can be, the arguments can be addressed through complex addressing scheme. So we have to implement some kind of instruction parser to see where these operands actually reside in memory. It's not that complex code, though. We implemented this nested virtualization for Intel, but we cannot share the source code for it because it's copyrighted. The nested virtualization actually has been implemented many years ago by the IBM System Z mainframes. It's very cool. But the manual says that it's not a good idea to use this nested virtualization feature in a production environment because it is intended to be used only for testing purposes. And also, a few weeks ago, we received an information that KVM project implemented nested virtualization for AMD systems. So I think it's not included in the mainline code, but it exists as a patch for the main KVM code. So if anybody interested, you can see how this nested virtualization is implemented in a real-world hypervisor. Bluepill boot. This is a project for illustration the possibilities of using the virtualized malware in a more complex way that it was used before when a new Bluepill was implemented. Bluepill boot is based on a Bluepill source code, or new Bluepill source code, but it does not require any particular operating system to execute. So it installs in the master boot record or maybe BIOS, it doesn't really matter, of the system. The demonstration was implemented, the proof of concept code was implemented in like an MBR infector. So it boots from MBR and it virtualizes the underlying operating system. So it really doesn't matter what this operating system is. It does not depend on any kernel, particular offsets in this operating system. It just virtualizes the OS from the very beginning. For example, if we run a Xen hypervisor with some guests, we can use, let's say, a shell on one of its guests, like we have a shell on VM2, and we somehow, the VM2 is not a privileged domain. Let's think that it is domain U. So it's user domain, which does not have enough privileges to override any original MBR. But if we have some backdoor, or if we found some vulnerability inside Xen or inside its management domain, DOM0, we can possibly ask this management domain to modify the MBR contents for us, and this is how we may install on the system. And on the next reboot, we will run a Bluepill, and the Bluepill will virtualize this hypervisor. So Bluepill boot consists of three major parts. It's MBR infector, a Bluepill loader, and a main Bluepill code that supports nested virtualization, because it is mandatory to support this nested virtualization if you want to run some hypervisor like Xen or any desktop hypervisor if the user runs some desktop hypervisor inside his operating system, like virtual PC. This is the disk layout of the Bluepill boot infected disk drive. So it overrides the MBR, and it stores the original MBR on sector number 2, just right after the original MBR, and it fills the 20 next sectors with main Bluepill code. Actually, this code is compiled by a C compiler, WDK compiler to be exact, and it is already a 64-bit portable executable file. So we have to implement some kind of a portable executable loader in Bluepill MBR just to enable long mode, and then use this loader to run the main Bluepill code. This is what happens when Bluepill boot is started. The Bluepill MBR gets this memory address at the beginning of this execution, and it's set to 7C00. It's always a constant. So then it assumes that the first megabyte of the physical memory is always allowed to be rewritten by any operating system loader. So it locates the main Bluepill's image at the address of 10,000 hex and copies the Bluepill boot code there. And it also enables long mode right in the MBR. So then it's Bluepill stage 1 receives execution, and it gets the map of the available memory using BIOS services in 15 and the function EA20. It gets the memory layout, finds some free space that it can occupy, copies itself there, relocates everything that it needs to be relocated, and then copies the original MBR stored on the sector 1 of the real hard disk to the memory at address 7C00, just to emulate the BIOS behavior. And then Bluepill begins to virtualize the original MBR in the real mode. This has been implemented for AMD systems because AMD SVM extension supports the virtualization of the real mode, while Intel VMX does not support virtualization of real mode. So we have to use some clever tricks to let the original MBR and original OS loader think that it still runs in real mode, while it possibly can run in virtual 86 mode. And we have to emulate certain instructions, not very many actually instructions, like moving to CL0 and reading from CL0 and so on, just to overcome this behavior of VMX that it does not support real mode virtualization. But it exists only in theory right now. it has not been implemented in Bluepill. But if you take Xen as an example, Xen implements this V86 mode emulation quite well. And this happens when original MBR begins its execution. Let's think that original MBRs begin to execute Xen code at some point of time. So we have typical configuration of the Xenified system. Like we have some management domain, we have Xen. So Xen starts its management domain, then the management domain instructs Xen to begin begin to virtualize a few guests. So when Xen starts, it has to query the memory layout map. Since Bluepill does not virtualize any memory, it has to intercept this query of this memory map. And this memory map is obtained by calling interrupt 15 in BIOS. And it has to modify the map so that not Xen, not any other operating system loader will overwrite the contents of this Bluepill memory. Because if this override happens, then it will most likely lead to a crash later on the next VM exit. So Bluepill informs Xen on each int15 call that a certain piece of memory is occupied by BIOS, and not Xen, not any other operating system loader allocates this memory later. So I will demonstrate a boot process of the Bluepill booted system. So this video was recorded on a live system, non-virtualized, of course. This is the beginning of this boot process, and you saw this. Let me show it again. You saw this blue frame around the screen. That just for debugging purposes, it informs the user that Bluepill boot activates right now, and then you see the grub loader screen, and that means that the system has been virtualized already, so that we saw Bluepill boot initialization, and later we see this Xen booting process. It will run shell in a little while. So this system is not configured to run any hardware virtual machines, hardware HVM domains, but it's not that important because Xen enables virtualization flag right at the beginning of its boot process. So you see that everything works fine, and the system boots quite well. Yeah, and just to demonstrate that Bluepill boot does not depend on any operating system in particular, let's see the boot process of the very same machine, but with Vista operating system. So I just switched hard drives, and infected Vista loader with Bluepill boot. You see the blue frame. There is a boot options screen showed by Vista. So one might think, how does static root of trust measurement or the dynamic root of trust measurement can be used against this type of attacks? And this is why we use Xen Bluepill, because it's a good demonstration that static root of trust and dynamic root of trust do not really help in the scenario when we attack the hypervisor, the already running hypervisor. Because of course you can notice some difference in the boot process if you run Bluepill from MBR, But if you